Okay, I hope everybody had a good day today. Today we are going to be focusing on two things. One, or the first thing we're going to be focusing on are resistors. Second thing we're going to be focusing on are loaded voltage dividers. We have previously discussed voltage dividers, and a voltage divider is simply a battery with two resistors in series, right? If we have a battery with two resistors in series, what happens to the voltage coming from the battery? It gets divided up amongst the two resistors, right? What if the resistors are the same value? Is it divided equally or is it divided unequally? It's divided equally. What if the two resistors are not the same value? Is it divided equally or unequally? Unequally. Okay? So a battery with two resistors in series, okay, which I'll draw, okay, is a voltage divider. Okay? That is considered an unloaded voltage divider. We're going to learn the difference today between an unloaded voltage divider, which we've studied in the past, and today, for the first time, a loaded voltage divider. But first, I want to talk some about resistors. For one reason, it's scheduled for this week in the lecture notes. If you're looking at the online materials, you'll notice that week number 3 is titled Resistors. And there is a rather thorough and extensive discussion about resistors, about the different types of resistors, and so on. I'm not going to spend the entire lecture discussing that because it is relatively easily understood if just read. Okay? First of all, a resistor is something that creates opposition to current flow. Okay? So when you read about resistors, you're going to read that the definition of a resistor is a device that creates an opposition to current flow. Okay? Something that has become somewhat of a mantra for us. Another component of resistors that is important to understand is that resistors come in all different shapes and sizes for all different types of applications and all different kinds of tolerances. In other words, you can pay a fraction of a penny for a resistor that has, let's say, a plus or minus 20% accuracy if you buy it by the train load. Okay? On the other hand, if you buy a resistor that is highly accurate, in other words, a resistor that has not a 20% accuracy, not a 10% accuracy, not a 5% accuracy, not a 1% accuracy, but a 0.01% accuracy, you can expect to pay a lot of money for that resistor. Okay? So it just depends on what your application is. If you need something to be extremely accurate and you're buying a resistor for that application, you're going to pay a lot of money for it. If you're buying something and it doesn't matter if it's plus or minus 20% off, then it's going to be relatively inexpensive. Another issue that I want to focus on and emphasize is that there are different kinds of resistors. There are carbon composite resistors. Carbon composite resistors just refers to the material that the resistor is made out of. There are fixed value resistors, in other words, resistors that are typically coated with a particular color scheme that lets you know what the value of the resistor should be and also what the tolerance of the resistor should be. In other words, tolerance, accuracy, is it plus or minus 20%, 10%, 1%, 5%, okay? And all of that is in a color code that I never take the time to explain in lecture, because it is something that is very difficult to absorb unless you do it in a lab exercise and unless you read it and you look at the colors. And because of the fact that we have limited ability with the video to distinguish between all of the different various colors in the color coding scheme, we won't attempt to do that on the board because that usually does not prove successful. One of the things that a lot of people don't come to grips with for a while is that resistors have various power ratings or various wattage ratings, okay? And as logic would dictate, a resistor, and I'm going to draw basically what a carbon resistor would look like physically. This is obviously a blown up version of it. I'll color it in with black. Okay? If this guy here was to represent a 1/4 watt resistor, okay, then what that would mean is that that resistor is designed to operate at 0.25 watts of power dissipation without overheating, without catching on fire, without fusing and burning up. In other words, it's designed to operate at that particular power level. Okay? There are resistors that are made that are 1/2 watt resistors. There are resistors that are made that are 1 watt resistors. There are resistors that are made that are 2 watt resistors, 5 watt resistors, 50 watt resistors, 100 watt resistors, 500 watt resistors, 5,000 watt resistors. And guess what happens every time the rating of the resistor increases?
Gets bigger.
The size of the resistor gets bigger. Because if the resistor has to dissipate more heat, there has to be more surface area in order for the air to cool the resistor. When we start getting into extremely large resistors, guess what we have to do in addition to making the resistor physically larger? We have to blow air across it. Okay, so we have to cool it with a fan. Sometimes we have to design cooling fins into the outer jacket of the resistor. Okay? And these are all things that become pretty much common sense once you have read the material from the textbook or a reference book on resistors, and you've done a couple of experiments with resistors. And so in terms of lecturing, I don't go too much further than that because it's really something that you need to put your hands on and you need to experience physically to really understand it. Okay? Difficult to understand it thoroughly just with a lecture. The other thing that I'll say about resistors is that it is always good practice to select a resistor that is larger than the value of heat dissipation than you expect in your circuit. Example. Let's say that we had a simple circuit consisted of a regulated DC power supply or a battery, and let's just say that it was 12 volts. And let's say that we had a resistor that was hooked up to this circuit, and that we expected this resistor to dissipate 1 watt. Okay? If we expect that resistor to dissipate 1 watt, and we want to make sure that this is a reliable circuit, in other words, it's not just a cheap circuit that it really doesn't matter if it fails, it's involved in something that can just sort of be thrown away and replaced at will, then the one thing that we're going to want to do is make sure that we select a value of resistance that is overrated. Okay? So if this circuit is being used for something that is critical, you know, something involving life support, something involving a, you know, heart-lung machine, something like that, right? Then if you know this is going to be dissipating 1 watt, you're not going to put a 1 watt resistor in there. You're going to put a resistor that's rated for significantly more than 1 watt. Okay? You're going to at least double it. And if it had something to do with anything involving life support or something like that, you would probably put, you know, a 5 to 10 watt high accuracy resistor in there. Okay? Because what happens is, if the resistor is dissipating 1 watt and you put a 1 watt resistor in there, you're taking that resistor to its maximum. In other words, a certain percentage of the time, that resistor is going to fail, even though it's rated for 1 watt. Okay? Just because of inconsistencies in manufacturing. Because of that, if it's a critical situation or a critical circuit, we're going to want to put a 5 to a 10 watt resistor in there so that the resistor runs more on the cool side, and there's really no chance that it's going to catch on fire, burn up, fail, whatever. Okay? You're also going to want to buy a resistor that is high precision and a resistor that is made of high quality materials. Okay? Another thing that I will mention about resistors, and then we'll move on to loaded voltage dividers, is that in most every lab, the lab next door included, we'll have one in this lab shortly, is a big chart on the wall. And the chart on the wall has all of the color coding that allows you to take a resistor, look at it, and determine what value that resistor is simply by the colors of the resistor. This, and I don't know if we can zoom in on this at all, this is a 1/4 watt cheap resistor. Okay? In large quantities, this resistor would cost less than 1 penny. In other words, if you were to buy 100,000 of them, you'd spend less than 1 penny for this resistor. Okay? So it's not something that you really need to worry about because it's not expensive, it's expendable. Now, probably difficult to see, even with my naked eye, difficult to see, there is a series of color strips on this resistor. And these color strips tell you what the value of the resistor is. Okay? Now, zooming in on this, you may or may not be able to differentiate between the color of the body of the resistor and the strips on the resistor. Okay? But by looking at the different strips on the resistor, we call that color coding, we can determine, number one, what the value of the resistor is. Is it 100 ohms or is it 50 ohms? Or is it 20 ohms? Okay? We can also determine what the tolerance or the accuracy of the resistor is. Is it plus or minus 20% accurate? Is it plus or minus 5% accurate? Okay? And all of this information that we need to decode the value of the resistor and its power rating is on a big chart. Okay? They also sell it in little handbooks that'll fit inside your shirt pocket. They also sell it so that you can load it on your computer. So all you have to do is type in 100, and then it'll tell you the colors that are supposed to correspond to a 100 ohm resistor. It'll let you go the other way. It'll let you type in the colors, and then it'll tell you what value of resistor would correspond to those colors. Okay? They also make calculators that have color coding built into the programming of the calculator. And so because it's so accessible, it's not something that I teach the way that I used to teach 10 years ago before, the technology made it so easy to not have to memorize, all of the colors. And there was also some politically incorrect ways that people memorize the colors, and so I most certainly, didn't even want to get into that, right? So I would suggest looking at it, at least understanding one of the acronyms that are used to memorize the color codes, because there are politically correct acronyms for the color codes as well as politically incorrect acronyms for the color codes. Okay? But then realize that you can buy a $12 calculator that'll do everything the chart will do and everything that memorizing all that information will do for you. Okay? All right. So that pretty much does it for resistors. Let's go now to unloaded voltage dividers. Unloaded voltage dividers. As we talked about before, an unloaded voltage divider, the simplest form, consists of a DC battery connected to two resistors that are in a series configuration. So if this is resistor 1, this is resistor 2, and this is the battery voltage, this would be an example of an unloaded voltage divider. An unloaded voltage divider. Okay. Now, a few things that you probably don't realize that I want to make clear to you right now, which will be test questions in this class, as well as aptitude questions on industry exams when you go to, apply for different jobs. Let's say that this resistor was 10 ohms, and this resistor was also 10 ohms. And just to make things simple, let's say this source voltage was 10 volts. Okay? If we were to draw an equivalent circuit to this circuit right here, the equivalent circuit would consist of one battery that had a 10 volt electromotive force, or a 10 volt electrical pressure, and one total resistance. And when we have series resistors and we want to find out what the total resistance is, our total, we just add them like money, right? It's called algebraic addition. So what would the total resistance be of the equivalent circuit of this unloaded voltage divider? 20 ohms. So it would be 10 plus 10, or 20 ohms. Okay? Now, watch this carefully. What I'm going to do is I'm going to switch colors. Are we okay with blue with our video? Okay. I'm going to switch colors here to blue, and I am going to transition this voltage divider from an unloaded voltage divider to a loaded voltage divider by doing one simple thing, and that is taking another resistor and placing it in a parallel connection with the bottom resistor in our first circuit. And we're going to call this the resistance of our load. Okay? So this is a loaded voltage divider. Okay? The part of the circuit drawn in black constitutes the unloaded voltage divider. The part of the circuit drawn in blue constitutes what loads the voltage divider. So this would be like connecting a toaster, or connecting a microwave, or connecting something that would draw energy, current, power, dissipate heat, all those things. Okay. Now, one of the things that is asked in a lot of questions is the total resistance of an unloaded voltage divider greater than or less than that same voltage divider with a load connected to it? Let me say that again. Is the resistance of an unloaded voltage divider, we figured out that that was 20 before we loaded it, okay? Is it greater or less than the total resistance of that same voltage divider when we connect a load to it? Okay? Now, in order to figure that out, what we have to do is we have to figure out how to combine resistors that are in parallel. So we're going to move back to the board to the left here, and I'm going to show you a formula that's going to allow us to figure out what that is. We know that if we have two resistors that are in series with each other, R1 and R2, and they're each 10 ohms, that the total resistance is equal to R1 plus R2, which is equal to 10 ohms plus 10 ohms, which is equal to 20 ohms. Right? Everybody straight on that? What if we reconfigure that circuit so that the resistors are connected in a back-to-back or parallel configuration? In other words, instead of being connected end to end, they're now connected back to back. This is called parallel. This is a parallel connection. So if this is resistor 1 and this is resistor 2, and we'll go ahead and leave them at the same values. Okay? We'll let resistor 1 be 10 ohms, and we'll let resistor 2 be 10 ohms. Okay? It turns out that there is an equivalent circuit, and that equivalent circuit consists of one resistor which has a total equivalent resistance. Okay? Let me show you how that works. When we had the series resistors, we found that the total resistance is equal to R1 plus R2 plus R3 and so on. Okay? In the parallel connection, it turns out that 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Okay? Now, when you simplify this using some basic algebra, which you don't have to do every time, you only have to do it one time. And once you've done it that one time, you can write it on your cheater sheet or your crib sheet, and you've got it there forever. Okay? So it's not some big mathematical quest that we're on here. What I'm going to do is I'm going to write the general formula for resistors that are connected in a parallel connection. Okay? And I'm going to switch back to black here for a second. It turns out that for parallel, resistors, R total is equal to 1 divided by the inverse of R1 plus the inverse of R2 plus the inverse of R3 plus the inverse of R4, and so on. Just keeps going on and on and on and on. So no matter how many resistors you have in parallel, you just keep on adding another inverse of that resistor. And it always, 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 always works the same. Now, there are other formulas that you can use as shortcuts if you have like only 2 resistors, or if all your resistors are the same value. Okay? But those are special case formulas. This works all the time. Okay? Can't give me a case where it won't work. So, let's go back to the problem, which I'm going to redraw over here. Let's go back to our loaded voltage divider. And what I'm going to do is I'm going to erase this. And I'm going to redraw the circuit that we started with. This is 10 volts. This is R1, which is 10 ohms. This is R2, which is 10 ohms. We know that that would be 20 ohms if we left it like that. And then we're going to load it with another 10 ohm resistor. So this is our load, which is going to be 10 ohms. Okay? Now, the first thing that we're going to do is we are going to calculate the equivalent resistance of these 2 resistors in parallel. Okay? To do that, I'm going to use the nomenclature R2, load. Why am I doing that? Because I'm combining resistor 2 and the load resistor. So I'm saying that's resistor 2, load. Resistor 2, load is equal to 1 over the inverse of 10 plus the inverse of 10. If you get your calculator out, if you can't do that in your head, what is that? 5 ohms. 5 ohms. It got smaller. 5 ohms. Resistors that are connected back to back or in parallel give you a smaller resistance when you total it up. That's why they draw more current. That's why when you plug in, 4 hair dryers instead of 2, you get twice the current. Because the resistance has gone down, and current is equal to voltage divided by resistance. So if the resistance goes down, the current goes up. In parallel circuits, when you connect more and more and more hair dryers, the total resistance of the hair dryers goes down. That means it's drawing more and more current from your circuit breaker panels. And that's why it's said that the load is increasing. Okay? Now, I'm going to erase this. And I want to come back to this for a moment. This formula is in your book, and you should definitely put on your cheater sheet or your crib sheet. But what I want to do is I want to focus on this for a moment. R2, load is equal to 5 ohms. Okay? Now, when I'm looking at this circuit right here, okay, that means that I can replace part of the circuit with a 5 ohm resistor. What part of the circuit can I replace with a 5 ohm resistor? How about R2 and R load? This guy and this guy. Does that make sense? So in other words, I can erase both of these resistors, and I can replace it with one resistor. Now that one resistor is actually the combination of R2, LOAD. But its value is 5 ohms. Okay? Now, if I were to figure out what the total resistance of this circuit is now, what do I have? Do I have a parallel circuit or a series circuit? Series circuit. And if I were to figure out what the total resistance of the series circuit is, what would I come up with? 15, because they add algebraically, right? This is a series circuit, and so the total resistance is simply going to be equal to 10 ohms plus 5 ohms, which is equal to 15 ohms. Okay? Now, if I erase all of those resistors and replace it with one total resistor, then I could call that R1, 2, load. Because it's really representing the effect of resistor 1 combined with resistor 2 combined with a load resistor. Right? That's what it's representing. It's the effect of all of those resistors working in combination with each other. And that has a value of 15 ohms.
Did you generally write it like that so people know that it's a series of...
I like to do that. You don't have to, but I like to do that. And the reason I like to do that is because it's an accounting method. In other words, I'm sure that I didn't leave something out. Okay? Or I'm sure I didn't put something in there that I didn't intend to put in there. Okay? It's not taught in a lot of books, but it's just a method I like to use. Okay? It is taught in some books. Now, let's move back over to the circuit that we started with over here on this board, which was our loaded voltage divider. Okay? And let me ask you this following question. What is the total resistance of our loaded voltage divider? And let's scan back over here. 15 ohms. Okay? Now, watch this. Let's scan back over to this circuit over here, and let's remove the load. Okay? If we remove the load, and I want to know what the total resistance is of the unloaded circuit, what do I get? 20. Okay? Now, I don't know if I stand like this, if you can see, but what's the difference between the unloaded and the loaded circuit? Can my video see both my right and left? Okay? All right. So, let me ask the following question. If I have a series unloaded circuit and I load it, does the total resistance go up or down? It goes down. Very popular question. Very popular interview question. Okay? A lot of people get that wrong because they think about pallets in the back of their truck. Well, if I put more load in the back of my truck, it's heavier. It's going up. The scale's going up. If I'm at the dump and I got more load in the back of the truck, I'm going to pay more money because the weight of the truck is higher and I got more load in there. In electrical circuits, it works just the inverse way. Why? Because loads are almost always, I would say 97% of the time, connected in parallel. And because they're connected in parallel, the total resistance goes down. Okay? Let me pause for a minute for questions, observations, comments. Is there anybody who didn't understand a certain part of what I just explained, or would like me to re-explain part of what I just did, or has a question? Fred.
How do you enter that formula into your computer? I mean, into your calculator?
Good question. Good question. How do you enter this formula right here into your computer? How in the world do you do that? That is a good question. Okay? Now, since we're capturing this on video, I'm only going to explain it really once, okay? Because you can rewind it. But my suggestion is, and there's a lot of ways to do it, my suggestion is the best way to enter it, and I'll move over here. Let's say that we have our total, which is equal to 1 over the inverse of R1 plus the inverse of R2 plus the inverse of R3. Okay? Then what I suggest doing, if you're trying to put this into your calculator, okay, and let's give it some numbers. Let's say that we had a circuit where we had 1 over the inverse of 10 plus the inverse of 10 plus the inverse of 5. Okay? The first thing, which doesn't come naturally, is you want to start in the bottom. Start with the denominator. Don't start at the top. Usually when we have a fraction, like 1/2, and we're putting it in our calculator, we put in 1 divide 2 equals 0.5. Okay? When you have this, the tendency is to put in 1 divide, what do I do next? Okay, you don't do it that way. The way that you do it is you put in this number right here. So you put in the number 10, okay? And then you press the key on your calculator that says x to the minus 1. Okay? What that does is it takes 10 and it inverts it. Gives you 1/10. Then you press the plus key on your calculator. And then you put in 10 and press x to the minus 1 again. X to the minus 1 again. Then you press the plus key. And then you put in 5. And you press x to the minus 1. That's a button on your calculator. So you put in 10, press x to the minus 1. Press plus. 10, x to the minus 1. That inverts it. Plus 5, x to the minus 1. That inverts it. Okay? Then you press the equal sign on your calculator. For some of you, that'll be inner. Some of you, the inner sign and the equal sign are interchangeable with each other. Now, when you press equal, what have you found? The denominator. You have not found the answer. You have found the answer in the bottom part of the fraction, which is called the denominator. So what do you have to do to get the final answer? You have to press x to the minus 1 again. And then in some calculators, you may have to press equal, depending on the calculator. Okay, now, from calculator to calculator, there is a little bit of variation. In some calculators, you have to do it just a little bit differently, but this is the general approach. For those of you that were following with me, what did you get for an answer? 2.5. 2.5. So this right here should be equal to 2.5 ohms. 2.5. Now I want you to notice a couple of things here. Okay? The most important thing is that in a parallel circuit, the total equivalent resistance is always, 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 always smaller than the smallest resistor in the circuit. Do you notice how the smallest resistor in the circuit was a 5 ohm resistor? And what did we come out with our total? 2.5. Okay? So if, let's just say, hypothetically, I were to erase the answer and change this 10 to a 2. Before anybody tells me what the answer is, what do we expect the answer to be less than? 2. What is the answer? 1? We have agreement with that? 1? 1 ohm? So the correct answer is 1 ohm. Do you notice how when I said, what do we expect it to be less than 2, it was less than 2? Okay? That's a good way to double check your calculations.
Or it'd be more like 8/10.
Did I get a wrong answer? Or were there other people checking?
1.25.
I get 1.2.
1 1/4? Okay. 1.25 ohms. And that would round up to 1 if you were rounding to the nearest ohm, okay? But is that still less than 2? Yeah, that's still less than 2. Okay? All right. Now, if I back up for a minute and we change gears, and I gave you a circuit like this. Let's say that the source voltage was equal to 20 volts. And let's say that I had 1, 2, 3, 4 resistors. Here's our 1, here's our 2, here's our 3, here's our sub 4. This guy is 10 ohms. This guy is 2 ohms. This guy is 14 ohms. And this guy is 71 ohms. Okay? First of all, before we do anything at all, what do we know that the total equivalent resistance must be less than? It's got to be less than 2. Got to be less than 2. Okay? So let's figure out how we would calculate what the total resistance is. Well, first of all, let me draw the equivalent circuit. The equivalent circuit would be the same battery, so it would have a total equivalent electromotive force of 20 volts, and it would have 1 resistor, and that 1 resistor would represent the effect of all 4 of those resistors. Okay? And we could either call that R1, 2, 3, 4. Notice how we're accounting for resistor 1, resistor 2, resistor 3, and resistor 4. And this is just a notation here. Or, in some books, you'll just see them call this R total. Okay? That's going to be equal to 1 over the inverse of this resistor, 10, plus the inverse of this resistor, 2, plus the inverse of this resistor, 14, plus the inverse of this resistor, 10. Okay? Now, in that previous example, we went through the keystrokes, but for those of you that are pretty quick with it, what do you get? 1.459. 13. Could it be 13?
1.45.
Couldn't be 13, right? 1.45, okay? So the total equivalent resistance is approximately 1.45 ohms. And do you see how that's a handy check? You look at the resistors and you verify that your answer is less than the smallest one. That also goes along with why the current gets big. Because current is equal to voltage divided by total resistance. As the total resistance becomes a smaller number, what happens to the current? It becomes a bigger number. So in parallel circuits, every time you add another hairdryer, you draw more current. Okay? Question? Okay. Have a good evening.